A postsynaptic potential. So postsynaptic is talking about the postsynaptic neuron. So this is after the synapse, and then this is a local potential. So this is going to be some change in voltage on a postsynaptic neuron. And there are two different types of postsynaptic potentials. EPSP, which is a excitatory postsynaptic potential. This is going to be anything that is going to increase the voltage. So we start at -70, that's resting. This is resting. Anything that is going to stimulate the cell and excite it is going to raise that potential and make it less negative, right? We're getting closer and closer to zero. And this is going to bring it closer and closer to that threshold of -55. This potential is not going to cause an action potential because it is not going to hit that threshold. But it does make that cell more likely to fire if another stimulus came along and then that one was able to get it to threshold. The other type of potential is an inhibitory postsynaptic potential, so an IPSP. And this is the opposite of an excitatory. This is going to inhibit a cell. So the way that we inhibit a cell is we actually lower its membrane voltage. So we started at -70. This is coming down to about -75 millivolts. That means it's got this much further to go before it hits that threshold of -55 millivolts. So that just makes it that much harder to stimulate this cell. It's actually hyperpolarized right now. Sometimes stimulation happens through a process called summation. This is where we add many potentials together to get to threshold. So if you look at this graph over here, you can see that there's 1, 2, 3, 4, 5, 6 stimuli before this cell finally gets excited high enough to stimulate an action potential. Sometimes summation is temporal, so meaning that they happen very quickly in time. So in this neural pathway here, you can see that there are many potentials happening very quickly. That's going to cause an action potential on this postsynaptic nerve. Down here, we can see spatial summation. So spatial meaning that instead of just having one cell, we've got 1, 2, 3 neurons all stimulating this. So this postsynaptic neuron here is receiving stimulus from 3 different locations, and that gives it enough stimulus to hit threshold and have an action potential. Sometimes there's actually even a third neuron involved, and that third neuron can either facilitate or inhibit. So in facilitation, here's our presynaptic neuron, and here's our post. The presynaptic neuron is exciting the post, but it's not enough to get to that threshold. But when you turn on this facilitation neuron, then this excitation is enough to go ahead and cause the action potential. So facilitation is going to enhance the effect of this presynaptic neuron. Inhibition is when it suppresses it. So in this situation, normally our presynaptic neuron would excite the postsynaptic neuron when the inhibitory is off. But if I turn on the inhibitor, that's going to turn off the presynaptic neuron, and it's going to eventually cause this to not have an action potential. So by turning on the inhibitor, we were able to turn off the postsynaptic cell. So how does our brain actually know what the signal means when it gets to its brain? One of the ways that we do this is through neural coding. So this is a pathway where the meaning of the action potential, so the meaning of the signal that's coming to the brain, depends on which path or which road it came down. So for example, close your eyes and press on your eyes just slightly, don't hurt yourself. What you'll probably see is bright spots in your eyelids, but you didn't actually see any light. What happened is that you put pressure on your eyeball, which caused an action potential in some of the neurons leading to your brain. And the only way your brain knows to interpret those action potentials is they came from your eye, so they have to be light. it has to be vision. So that's an example of a neural coding pathway, is that the information your brain receives from your eye, it interprets as vision rather than pressure. We also see that neurons don't just function as one-to-one, they can function in neural pools. So here we've got one input leading to many different outputs. We can have many different inputs that lead to a single output. We can have neural pools that come back and cycle back on each other to help itself amplify, as well as parallel discharges that send signals down different lengths of pathways, so that the signal comes on the output at different times depending on the length of each pathway. So our neural system is a lot more complex than just a presynaptic neuron and a postsynaptic neuron. This also has influence on the way we remember things. So the actual physical component of memory is the pathway, the nerve pathway through the brain. It's called a memory trace. And we have different levels of memory. Immediate memory is just the ability to hold something in your mind for a few seconds. So read that sentence. Literally, it says immediate memory is the ability to hold something in your mind for just a few seconds. If you had completely forgotten the beginning of the sentence, by the time you had reached the end of the sentence, you wouldn't understand what that sentence said at all. So immediate memory is really just the ability to kind of look at an entire sentence and remember the whole thing. And it lasts just a fleeting few seconds. By the time you move on to another paragraph, you've probably forgotten all of the specific words in this sentence. Short-term memory is something that you can quickly forget if you don't continue to put it into working memory, if you don't continue to use it. So, for example, remembering a phone number. Most people can only remember about 7 bits of working memory at a time, which is convenient because most phone numbers are 7 digits long. But when you add in an area code, it becomes harder to remember. I don't have any problem repeating 7 digits of a phone number back to myself enough times till I actually dial that phone number. But if I have to dial an area code too, I usually have to type in, 4 or 5 digits, and then I have to go look at the phone number again and then type in the rest, because I'm not able to hold 10 digits in my memory at one time, because our working memory is so small. This is also why remembering how to do math problems is very difficult, because you have to remember so many different things to remember how to do a math problem. Sometimes working memory can last for several hours, where you can recall what you remembered. So this is common if you hear a conversation, or you have a conversation with somebody and you go home and you tell somebody else about it, and you can usually remember a couple hours later exactly what you said in the conversation. But if you ask 3 days later what was in the conversation, you're going to have a harder time remembering the exact words. You might remember the gist. Working memory and short-term memory works because what happens is the pathway that you used when you heard the conversation for the first time refires when you remember it. But 3 days later, you have a harder time refiring that exact pathway and remembering exactly what was said. Long-term memory can last up to a lifetime. So if we recite things in working memory over and over and over again, we might actually be able to convert them to long-term memory. Long-term memory can be explicit or implicit. So explicit is when maybe you're taking an anatomy test and you need to remember something you learned. So you search your brain trying to find the thing that you remember. Implicit might be a memory that just comes up without you needing to search for it. So if you walk into a room and you smell a smell and it just triggers a memory for you, that's an example of an implicit memory. So take a moment and distinguish between an IPSP and an EPSP. What are the differences?